So we've seen before what happens if we place a charge in a magnetic field, it experiences a force. We've seen that a wire carrying a current I creates a magnetic field. So now our next question is, what if we have a wire with a current I and we place that wire in a magnetic field? So question, what happens if a wire with a current is placed in a magnetic field? And as we saw in the video just before, that the answer is it too will experience a force. And of course, the next question is, can we derive an equation that describes that force? Before getting to that, let's look at a wire as a current as some moving charges. So this picture shows a wire, and these circles represent the charges, and it has some current I flowing to the right. If we wait some time delta t, those charges will move. So for example, this charge will now be over here. This one would be here. This one would be over here, and so on. And so these charges will have moved. So our charges move. And in the picture we're told they move some distance L. So now we know from before that the force on an individual charge is given by the Lorentz force equation, QV cross B. And our task now, I'll move this up, is to see if we can modify this equation to describe a current in a wire placed in a magnetic field. And our first step in doing that is seeing if we can rewrite the charge. So remember, by definition, current is defined as charge per time. And for us, we're told that some amount of charge Q in our wire has moved, and our time interval again is at delta t. In a minute, you'll want to solve this equation for Q. The next step, though, before that, is seeing if we can rewrite our velocity. And so for that, remember that the definition of velocity is distance divided by time. So what you should do in your groups now is solve the first equation in example 1 for Q, and then see if you can rewrite velocity equals distance over time in example 2 using the variables given in this problem. So solving the equation I equals Q over delta T for Q is simply done by moving the delta T to the other side, and we find that Q is equal to I, the current, times delta T, our time interval. For example 2, where we had to rewrite velocity equals distance over time, using the variables in this problem, our velocity is simply v. We're told the distance the charge moves is L, and again the time interval is delta t. But remember, velocity is a vector quantity, which means on the right-hand side, one of these must be a vector as well. It cannot be delta t because time is never a vector quantity, so it has to be this L, this distance. So L is a vector quantity, and like all vectors, it has a magnitude and direction. The magnitude is simply the length of the wire. Length of wire. The direction is the same direction that the current is moving. So direction is same as the current direction. Now that we have these two expressions, we can substitute them into our Lorentz force equation. So down here we have FB equals QV cross B. Rewriting this, for us, it's a charge capital Q moving, We still have V cross B. And at this point, you'll want to pause the video, substitute in your expressions for Q and V that were just found, simplify the equation, and see what you get. Substituting in our expressions for Q and V, we find for Q, we have I delta T, and for V, we have L over delta T. We still have the cross B here. We see immediately that our delta T's will cancel, and what we're left with is that the magnetic force on a wire carrying a current I of length L placed in a magnetic field B is given by IL cross B. So we'll want to put a box around this equation and then write ourselves a note reminding us of what we just found, which is the magnetic force on a wire with a current I and length L in a magnetic field. And so force, as always, is a vector quantity, and we need to know its direction, and that's simply found using our right-hand rule for cross products. So direction is found using right-hand rule for cross products.